All right, class, we're going to take a look at some more rational exponents. And a rational exponent looks like an exponent that's a fraction. Fraction exponents just utilize our excellent formula where we've got a base to the x over y power that can be rewritten to be the y index root of that base to the x power. And so as long as you remember that the bottom part of the exponent is the index on the root, we will be doing well. So we make this, rewrite it to be the cube root of 64. And as soon as you rewrite it, we should be familiar from our previous lesson to just know that the cube root of 64 is 4. Or you could just type this in your calculator. So here we have a 1/4 power, and we have a negative sign on the outside. Notice here the difference where the negative's on the inside of the parentheses. The key here, the trick here, is recognizing that the 256 is the thing that's being raised to the 1/4 power, not the negative sign. So don't let your eyes be led astray. We are supposed to rewrite this as the negative 4th root of 256. It's just the 256 being raised to the 1/4 and then the negative afterward. The 4th root of 256 should be 4. And then you put that negative sign out in front. And then what you want here is to recognize that this is now the 4th root of a negative 256, and we cannot take an even root. So this is an undefined value. We don't pull out an I here as a 4th root, so we're just going to stop there and say that problem is undefined. So continuing, this, anytime you have a 1/2, it's just a square root. You can put the 2 here if you choose. You don't need to. If there's no number there, there's an invisible 2. It's imagined. And so there's just the square root of 100, which is 10. Then we have a negative on the inside, but that can be okay as long as this is an odd index, and it is. So 5 root of negative 32. That's the 5th root of negative 32. Sorry, I was supposed to write a 2 there. And that value, the 5th root of 32 is 2. You can check that on your calculator, but the negative sign goes out in front because it's just anytime it's an odd root of a negative, it just produces a negative result. And again, that's because the 2 to the 5th is 32. If you put a negative in there, it would give you a negative 32. So it works. And then down here, the cube root is what we're going to do there. The 1/3 power turns into a cube root. So this is rewritable as the cube root of 1/8. Anytime you have a root and a radical over a fraction, you can just separate that to be the cube root of 1 over the cube root of 8. Just treat them separately and bring the answer back together. The cube root of 1 is 1. Cube root of 8 is 2. The result of this is 1/2. That is 1/8 to the 1/3 power. It's just the cube root of 1/8. So now we're going to evaluate functions that have the m up there. Now I wrote it earlier as b to the x over y. It's the same thing here. A to the m over n is just the nth root of a to the m power. So as long as you've got something raised to a fraction power, you can rewrite it. They're the same things as long as you're keeping the positions right, just like so. So they're saying the same thing. The idea here is that this is the 2nd root of 36 to the 3rd power. And so there's 2 ways to do it. When you have the index rewritten, you can do the index before or after raising the base to that power. I said the word base because I like to see it as a b. It is a base, something being raised to a power. But again, the point is that we can do it this way, or you could rewrite it to be the nth root of a, and then on the outside to the m power, or the way I had it originally, you could say it's the y root of b to the x power. And so again, the order matters because here, I don't know what 36 to the 3rd power is, but I do know what the square root of 36 is. And the square root of 36 is 6. And then I could take that to the 3rd power. And so I have 36, 6 to the 3rd power, which should give me 216. When we take the 125, we could rewrite this to be the cube root of 125 to the second power. And again, I don't know what the 125 squared is, but I do know the cube root of 125 and then squared. The cube root of 125 is 5 because 5 to the third is 125. And then I know that 5 squared is 25. Working this problem as opposed to the problem below it, the negative stays outside. So this rewrites to be the square root of 4 to the fifth power with a negative on the outside. Now I'm going to do the square root of the 4 first and then do the fifth power. So the square root of 4 is 2, and then we rewrite it to the fifth power with a negative on the outside. So the 2 to the fifth is 32, and then keep your negative with it. The final answer will be negative 32. Whereas the next problem will be undefined because the negative 4 is on the inside of the square root, and we cannot take the square root of a negative unless you pull out an I. And we're just going to write undefined for now. Continuing with some more, we have odd with a negative on the inside, odd index that is. So we have a cube root of negative 27 and then 27 and then squared. We can put the square on the outside first because the cube root of 27 is 3. The negative sign stays with us, so it's negative 3 squared, and negative 3 squared is going to be 9. So this time, if you lost the negative, you would have got lucky because the answer would have worked out. But we do want to be intentional about whether or not you've got that negative sign working for us. Here, we have an even index, so we're going to say that this is undefined. Anytime you have an even index, even denominator on that power, you'd rewrite to be a square root of a negative 100, and then to the third power. We can't do it because the even index will not allow it. We could pull out the I. You can make this an I, and then a 10I, if you will. And then we could raise that to the third power, but that's a whole conversation for complex numbers where we're raising an I to the third power and coming out with a subsequent result based on what I to the third power is. When we have 16 to a negative exponent, what we want to do is take that negative exponent and understand that that is a property we learned early in our math career, I hope, where anything to a negative 1 is actually 1 over that thing. And so what we want to do here is make this 1 over 16 to the negative 3/4. Sorry, the positive 3/4. That's the point of flipping it over, is to make it positive. So we make it positive by flipping. And then we evaluate. So this will be 1 over the 4th root of 16 to the third. So the whole key here is that it's all just happening down. The negative brings it down below the fraction bar. So continuing, the 4th root of 16 is 2, so it's 1 over 2 to the third. Final answer, 1 over 8. And in like manner, this next problem, to get this to work with the negative, is you flip the inside over. So this will be 27 over 8 to the positive 3/4 power. If you flip the fraction, the sign changes. And then we rewrite this to be the 4th root, because it's a 4 in the denominator, 4th root of 27 over 8, and then all that to the third power. I'm going to save that third to the end because I don't want to get my numbers big at the beginning. So the 4th root of 27 doesn't work. The 4th root of 8 doesn't work. And so sure enough, I actually have to write it as 4th root of 27 over 8. And I do have to go in there and cube them. All right, so this one won't simplify nicely. So we're actually going to stop right there with it. And the issue is that there's no 4th root of 27, and there's no, if you raise 27 to the third power and then do the 4th root, it won't work out either. Same thing with the 8. We could rewrite it and simplify it, but you might as well use your calculator at that point. So we're just going to put a pin in that one, and then move on to this next one here. And we can understand that when we're multiplying bases, notice they're both 2's, you add the exponents. And so that's using our exponent rule. So we have 2 to the 1/2 plus 1/4 power. So this will turn out to be 2 to the, and then we got to make common denominators here. So top and bottom by 2. So this will be 2/4 plus 1/4, which rewrites this to be 2 to the 3/4 power. And then if we're supposed to leave it in exponential form, this is what you'd write. And then if you're supposed to write it in index radical form, we say 4th root of 2 to the 3rd power. And just like that last one that I showed us, this doesn't simplify, so we're just going to leave it right there because this number on the outside is bigger than that number on the inside, whereas the example before just wouldn't reduce clean. Now, our quotient of bases, here we have the 5's are both the same base. We can rewrite it using subtraction of exponents. So that turns out to be 5 to the 2/3 stays on the top, so 2/3, and then anything on the bottom is a negative exponent, so minus 7/3. By negative exponent, I mean to bring it up, you need to make it a minus sign. And so this will turn out to be 5 to the negative 5/3. And because the result is negative, you want to bring this back down. So we want to rewrite it, flip it to make it the reciprocal, 1/5 to the 5/3, which you can rewrite to be the 1 over the cube root of 5 to the 5th. Now we can reduce powers and do something with that and pull a 5 out, but we're just going to leave it there for now. Here we have a 4th power on the outside. We want to distribute that in. When you distribute powers, you multiply. And so this is going to turn out to be x to the 4/2 times y to the 8/3, and then over y. Now this y on the bottom, we want to call it a y to the 1 because we're going to bring it up here to subtract from this y. So x to the, I'm going to reduce that to be 2, and then y to the 8/3, and then we're going to say minus 1. Now that 1 needs to turn into a 3/3 so that I can subtract. That's going to be x squared times y to the 5/3. And then we're going to leave it like that, or you could rewrite it to be x squared times the cube root of y to the 5th power. Another one here, we have a negative exponent. So first thing I like to do before distributing this guy, I'm going to simplify vertically as much as possible. Notice I have negative exponents. I want negative exponents to go down and become positive, and this one that's on the bottom to go up to become positive. So this will, on the inside, rewrite to be x to the 4 times x to the 2nd over y to the 6th times y to the 1/3. And then it's still to the negative 2/3 power. Then I'm going to clean up on the inside. This will be x to the 6th because you add exponents when you have the bases being multiplied. Same thing here. We're going to have over y to the 6th plus 1/3. And then the whole thing is still to the negative 2/3 power. Now this 6 needs to become a 18/3 so that I can add denominators. So that on the bottom is going to be a 19/3 because 6/3 plus, or sorry, 18/3 plus 1/3 gives me that 19/3. So that's just scratch work. But this is going to turn into 19/3. And then I need to flip this. And then I get y to the 19/3 over on the top divided by x to the 6th. That causes this outside exponent to be a positive 2/3. So now that it's positive, I can distribute it in. I could have distributed it and then flipped at the end. It doesn't matter in the end. Either way will work. That negative sign would be taken care of now or later. I just did it now. So we distribute this in. So this is going to be y to the 19 thirds times 2 thirds over x to the 6 times 2 thirds. And then we just have to simplify. So working this out on the top is going to turn out to be y to the 38 over 9 divided by x to the, if I multiply this together, it's going to be 12 over 3. And just saving myself a step in rewriting, that's going to be x to the 4th. And that's as far as we're going to take that problem. You could rewrite the top one as an index if you wanted to, but we'll just leave it as a simplified exponent. Now, we have roots of roots problems where you've got subsequent indexes. All we have to do is understand these are fraction exponents, starting with this most basic one on the inside. So this is really just an x to the 1/4. If you just look at them one at a time, this inside most one is just an x to the 1/4. And then throw parentheses on that, and then you can look out another layer. Now it's to the 1/3 power. And then now we look out one more layer, that's a 2, a square root. So you put parentheses around that, and now it's to the 1/2 power. So this is really just x to the 1/4 to the 1/3 power to the 1/2 power, which ultimately just turns out to be x to the 1/4 times 1/3 times 1/2. When you have powers to powers to powers, you just multiply those powers. The final answer is simply x to the 4 times 3 is 12 times 2 is 24, 1/24th power. And you could leave it like that, or rewrite it as the 24th root of x. In an application problem, we are given a formula. T of d is the function. Time in terms of duration. D is the diameter. And so we're trying to figure out how long it takes for this storm to pass. So we got to find duration of the storm, given a diameter, and we're supposed to round to the nearest tenth of an hour. So we're plugging in the 16 and then just working it out. This is really a calculator problem. 0.07 times the 16 they gave us to the 3/2 power. Now, when you go to type this into your calculator, you can actually do, you can do it on like a phone calculator or a scientific calculator, but my favorite is to use Desmos. When you type it into Desmos, you go 0.07 and then open parentheses, and we've got 16, and then you do up arrow, and you can actually just open parentheses and put whatever fraction you want. Our fraction was the 3/2 power, so we just say 3 divided by 2, and then it just kicks out the answer for you, 4.48. So there's lots of different calculators out there, but most of them, if you're looking for a button that will do this, it looks like a y to the x button. So here on Desmos, if you click, it's got a to the b power is what it looks like here. I've seen a lot of calculators that say y to the x, but that's the button you're looking for there, and you can just type in a fraction in parentheses on any scientific calculator. So 4.48 will get us that result. So 4.48, and it says nearest tenth of an hour, so 4.48 should turn into our 4.5 hours.